All right, good afternoon, everyone. We'll record lecture 21 now. And when we left off in the last lecture, we were talking about A values, which are these, essentially the values of gauche interactions in substituted cyclohexanes when you have a substituent that is in the axial orientation. So let me just write that down to remind you. Okay, and so we said that for monosubstituted cyclohexanes, when you have a substituent, you can have two chairs where it's sitting in either the equatorial or the axial orientation. The axial orientation suffers from what we call A13 interactions. Sorry, not A13, I'm mixing that up with another one. Diaxial interactions, 1,3 diaxial interactions between the two axial hydrogens in the ring, on the same side of the ring, okay? And we said at the end of class that this diaxial interaction is actually just a special type of gauche interaction that we saw with N-butane, okay? And so that interaction is destabilizing. It imparts an energy difference to the two conformers. And the degree to which this increases is going to be defined as the A value. So this conformer for R equals methyl is about 1.8 kcals per mole higher in energy. And so the equilibrium between the equatorial and the axial conformers greatly favors the equatorial conformer. And because this is so common, we sort of call these changes in free energy A values. And so we say that the A value of CH3 is 1.8, okay? But it's important to remember that what we're talking about is, more specifically, is the energy difference between the equatorial and the axial conformers, okay? So the discussion in the last class was limited to monosubstituted cyclohexanes. More often than not, you're going to have multiple substituents in the ring, and so you need to be able to assess the changes in free energy when you change the orientations of those substituents. So okay, and so we'll focus this initial discussion on disubstituted cyclohexanes. And there are two ways to kind of bin the scenarios here. So one is the case where the two groups do not interact, okay? And specifically, that's going to mean when they don't both occupy an axial conformer in the or an axial position in one of the conformers. And so if we consider, let's consider as an example, 1,3-dimethyl cyclohexane. So I will draw it like this. Okay. Here, the two methyl groups are considered not to be interacting with one another. And I can draw a chair flip for this molecule. And remember, the key point with the chair flip is that the axial substituents go equatorial and vice versa. So okay, and it may be helpful to number carbons so that you can follow what's happening. So call that C1, call that C3, and there's 1 and there's 3, okay? And so the question is, what, if any, free energy difference exists between these two conformers? And you may be able to say right off the bat, well, they both have one axial methyl group, so they should be equal in energy, and that's the correct answer. If you wanted to sort of approach this systematically, you could say, okay, in the conformer on the left, what types of destabilizing interactions do I have? Well, I have an axial methyl. We know that that's worth about 1.8. And on the one on the right, I've also got an axial methyl, also 1.8. So the net effect is that the delta G here equals 0. The two conformers are going to be equal in energy. And so that's a very simple case. Another case is where you have two substituents non-interacting, but they're different. And so an example of that would be terpbutyl methyl cyclohexane. So let me draw that. Okay. And so you can have two chair conformers for this. What we can do is flip the cyclohexane, send all of the equatorial substituents axial, and send all of the axial substituents equatorial. Okay, and you get to something like that. And so this is a very different scenario because the nature of the axial substituent in each conformer, of course, is different. And so on the left, I've got a methyl group axial. On the right, I've got a terpbutyl. But we can still do a surprisingly accurate calculation of the relative of the energy difference between the two by considering the A values for each substituent. And so the methyl group is 1.8. And the A value for a terpbutyl group is quite large. It's about 5 kcal. So, okay. And so the free energy difference then is just given by delta G equals, again, product minus starting material, which equals 5.0 minus 1.8 which is going to be 3.2 kcals per mole, okay? And so the conformer where I have the tert-butyl group in the axial orientation is less stable by 3.2 kcals per mole. And so it's important just to note that we're talking about relative free energies, not absolute free energies. The only, this is going to be a common scenario when we talk about conformations of cyclohexane. We also saw this, if you think back to the acyclic conformational analysis with ethane and butane, we always just talked about, the eclipse conformer of ethane, for example, is 3 kcals per mole higher in energy than the staggered one. It's always relative because we're talking about equilibria. All right, so those are the two flavors of analysis when the substituents don't interact with each other. When they do interact with each other, things get a little bit more complicated, and the quantitative analysis is not really feasible. So okay, so for example, if we were to consider the example on the last page where we had methyl cyclohexane, this is actually from last lecture. So methyl cyclohexane, we said that this was plus 1.8 kcals per mole higher in energy than the equatorial isomer. Okay. So you might imagine if I replace one of those axial hydrogens in the left conformer, I'd get to 3.6, but it's bigger than that, and it's actually about 5 kcals per mole. So if I have two substituents and they can both occupy an axial orientation in one conformer, we say that they are interacting okay. There's a very bad steric interaction between these two methyl groups, also with the remaining axial hydrogen, okay? But that interaction is worth more than just two A13 values. I keep saying A13, I'm sorry, that's a totally different steric interaction. Two A values of the methyl group, and so this is uphill by about 5 kcals per mole. Okay, and you might be able to intuitively appreciate this. You can imagine, the 1.8 here on the top derives from the interaction of that methyl group with two hydrogens. Okay, whatever the value is worth for the structure on the bottom, the methyl group is interacting with one hydrogen plus another methyl group, and so it's a much more destabilizing interaction. And so we won't ever ask you to, apply numbers to these types of substrates. We will expect you to be able to identify the more stable conformer. And for the cases where the substituents are non-interacting, or there is only one substituent, it's reasonable to expect that you could use A values to calculate the energy difference between the conformers, okay? All right, so the next topic is going to be stereochemistry in cyclic systems. And I just want to preface this by saying there are advantages and disadvantages to every representation of a molecule. So in other words, when I draw cyclohexane flat with the line wedge diagram, that has certain advantages. It's fast, it's efficient, and as I'll show you, it's much easier to see elements of symmetry in the flat drawings. When you go to the actual 3D chair representations, that of course is more accurate. That better describes what's actually happening. But the logistics of drawing and interpreting those structures are a little bit more challenging. So we're going to do both here because it's important to need to flush out a couple issues. But on balance, when you're thinking about chirality and stereochemistry in substituted cyclohexanes, looking for elements of symmetry, it's much easier to go with the line wedge diagram than it is the chair. And so let me just get right into it. All right, so we'll start with 1,2 disubstitution, and we'll keep it simple. We'll just have a dimethyl cyclohexane. Okay, so the first thing we need to do is define what we call cis and trans. And so the term cis in this context means that the substituents are on the same side of the ring. The trans would be opposite sides of the ring, okay? And so this is cis. This happens about a half dozen times a day. She sits up and then takes a header, and you can usually hear it. It's not good. More startled than hurt, typically. All right, cis 1,2 dimethyl cyclohexane. So the methyl groups are on the same side of the ring, and we can ask the question: is this molecule chiral? Right? I would put it to you: are there stereocenters in this molecule? Okay, the answer is yes. Both of these are stereocenters. Okay, and we can go ahead and define an absolute configuration if we want. If we're looking at the bottom stereocenter, this is priority 1, this is 2, this is 3, and so that is S. And if we look at the top, this is 1, this is 2, this is 3, so that is R, okay? But is the molecule chiral, okay? And this is where the line wedge diagrams are very helpful. Hopefully you can see that there is a plane of symmetry right down the middle of this molecule. So okay, so by looking at the line wedge diagram, I can see, and hopefully it's quick for you all as well, I can see that the molecule itself is achiral, okay? Of course, that's not the actual conformation. It's not flat, right? So we want to draw the chair conformers And this is where it can get to be a little bit misleading. So if I draw a chair conformer, and again, I'm going to sort of start arbitrarily with one conformer. I'm going to maintain the same absolute configuration. So there's a CH3 up, and there's a CH3 up. Okay. And let's give the carbons numbers so we can keep track of everything. Let's call this A and B, A and B, okay? So if you look at this molecule in 3 dimensions, it doesn't appear to have a plane of symmetry, right? Because those methyls are sort of going in different directions. They're not parallel as they look in the line wedge diagram. And so perhaps this molecule is chiral, right? Perhaps it's actually not meso. How do we test for that? The rigorous way to test for it is to draw an enantiomer and see if you can superimpose it. So why don't we go ahead and do that? Okay, so there's the enantiomer. Here's carbon A, here's carbon B. And if you play with this, what you'll find is that you can't superimpose these. Okay, so right away there may seem to be a contradiction. It looks like from the line wedge, I've got a mesostructure, but from the chair representation, I've got a pair of enantiomers. So the meso is telling me the molecule is not chiral. The chair representation is telling me it is chiral. Obviously, it's one or the other. What's going on? And the answer is that you have to remember that this thing can chair flip. And so if I flip the right-hand structure, okay, I'm going to get to something like this. All right, and now position A is going to bear an equatorial methyl group and an axial hydrogen, and position B will bear an axial methyl group and an equatorial hydrogen. Okay. And so what I want you to see, hopefully you can see this, is that if I take this conformer on the right and rotate it around, okay, I can actually overlay position B with position A in the first one and position A with position B in the first one, okay? And so these two molecules, because A and B are equivalent, right? There's nothing else to distinguish them. These are identical. Okay, and so what we would say is that just considering the chair representation, this molecule does not possess a non-superimposable mirror image. The mirror image is in fact superimposable. All I have to do is a chair flip. And because it has stereocenters, it is in fact a meso compound. So a compound with stereocenters, but overall achiral. And don't let the chair flip, throw you for a loop. Remember, conformational isomers are their own sort of category, and they've up to this point been defined as isomers that are interconverted by rotation about a single carbon-carbon bond by facile rotation, an example being staggered and eclipsed ethane. Here we're extending that definition to saying that conformational isomers are those that can be interconverted by a chair flip in the case of cyclohexane, and these chair flips are rapidly occurring at room temperature, and so we need to consider that in the stereochemical analysis, okay? And so this may or may not be clear. Hopefully, between the lecture and the text, you can make sense of this. But again, if you really want to sort of get to the answer quickly, it's best to look at these things in the line wedge representation. Even though that's less accurate, it's a less accurate depiction of reality, it's much quicker to determine if there's symmetry in the molecule or not, okay? All right. So I'm gonna pause I'm gonna stop the recording and then we'll pick up in just a second here.